Welcome to the EvoEd COVID-19 video series. In this video, we'll discuss the origins of SARS-CoV-2 in humans. Then, we'll take a look at the phylogenetics and the overall evolutionary history of the virus. By the end of this video, you should be able to describe the SARS-CoV-2 origin hypothesis of zoonotic spillover, and you should also be able to read a phylogenetic tree in order to describe the evolutionary history of the Delta and Omicron variants. Where did SARS-CoV-2 come from, and how did it get to humans? Well, we know with near certainty that all recent novel coronaviruses descended from a strain that was isolated in bats. But describing how it then made its way to humans isn't so simple. The leading hypothesis is that it made its way to humans through a zoonotic spillover occurring in the wet markets of Wuhan, China. A zoonotic spillover is when a virus jumps from infecting one animal species to another. This, of course, requires close contact between the two species, but also typically involves some sort of mutation that makes the virus effective at infecting the novel host. In the case of the two previous novel coronaviruses, SARS-CoV-1 and MERS, we have good evidence that these viruses jump from bats to an intermediary host and then to humans. However, scientists haven't been able to yet identify an intermediary host for SARS-CoV-2 with the same degree of certainty. So, as of now, any hypothesis regarding the origins of SARS-CoV-2 is a valid one. However, regardless of if zoonotic spillover was the cause of SARS-CoV-2 in humans or not, it's important to be aware that spillover remains a very real risk factor for future pandemics, and we need to consider how environments such as wet markets create high-risk conditions for spillover events to occur. Now let's take a look at the evolutionary history of SARS-CoV-2 from its origins to present day by looking at a phylogenetic tree. A phylogenetic tree is a diagram that displays the evolutionary relationships between different organisms. Phylogenetic trees are constructed by sequencing the genomes of many samples and then comparing the similarities between those genomes in order to estimate the relatedness between the organisms sampled. The way you read a phylogenetic tree depends on its orientation. For the tree here, we'd read it from left to right, where moving further to the right means we're moving further ahead in time. Typically, the rightmost of the tree represents present time and lists species that are currently existing. Here, those species are represented from A to E. The root of a phylogenetic tree is the evolutionary origin of all other species depicted on the tree. In other words, all the species listed A through E once shared a common ancestor that is depicted by the root of the tree. A node represents a point where a single lineage branches off into two. In other words, a point of divergence. For example, the node at letter Y is when a lineage diverged into the lineages that would eventually become species C, D, and E. Lastly, a clade is a section of a tree that contains an ancestral lineage and all the descendants of that lineage. So node X, along with the descendants that follow it, species A and B, represents a clade. Here is the phylogenetic tree of SARS-CoV-2 as of March 2022. If we look at the bottom left, we can see the origin of SARS-CoV-2, which was first isolated and sequenced in early 2020. Although the virus had already begun to spread towards the end of 2019. All current variants of SARS-CoV-2 are descended from this initial strain. About a month later, we can see the first major node or divergence event that led to two separate lineages. The Alpha and Omicron variants are the descendants of one of these lineages, while the Delta variant is the descendant of the other. In February 2021, the Delta variant was first identified and sequenced, and months later it became the overwhelmingly dominant variant worldwide for almost the rest of the year. However, near the end of 2021, Omicron was first identified and sequenced, and it globally became the dominant variant even quicker than Delta did. In fact, it spread so rapidly that it largely displaced Delta. As of the recording of this video, Omicron largely remains the dominant variant of SARS-CoV-2. But there's one more interesting thing to look at when it comes to Omicron. Let's go back in time a bit and take a look at the left side of the tree again. The last common ancestor Omicron shared with any other variant of the virus was back in early 2020, before the pandemic was even called. This means that this lineage that eventually led to Omicron went undetected for nearly 2 years. So where did Omicron come from? How is it possible that a variant which is proven to be so transmissible go undetected for nearly the entire span of the pandemic? Well, there are a few hypotheses as to what happened here. Firstly, since we need to sequence the genome of a new variant in order to identify it, it's possible that the Omicron variant evolved in a relatively isolated population that didn't have contact with larger populations where genetic sequencing may take place. Another possibility is that the virus spilled over from humans to another animal species and then back into humans. So the evolution of Omicron could have taken place within such an animal population before jumping back into humans. A final possibility is that Omicron evolved within an immunocompromised individual, such as someone with HIV. If the body is unable to eradicate the virus, then it can continuously replicate. Therefore, it's possible that an immunocompromised individual could have acted as an environment for the virus to freely evolve for months before passing it on to another individual. So, what does the future hold for the evolution of SARS-CoV-2? Well, we all saw how quickly Omicron became the dominant strain of the virus, and by the time you're watching this video, it's possible there'll be a new dominant strain. We can't perfectly predict the evolutionary trajectory of the virus, and the only certainty is that it will continue to evolve. An optimistic outcome is that the virus will continue to become less virulent, and as we gain increased herd immunity, it will eventually become endemic like the common cold. Fingers crossed.